Good morning, everyone, and welcome to the IC seminar. It is for me a great pleasure to introduce this seminar by Savita Mathur, Ramon y Cajal Fellow, that joins the IC about this summer, last summer, so starting. And it is for me a great pleasure, especially because I first met Savita some 15 years ago when she was finishing a degree on telecommunications engineering in Paris. And she feels somehow attracted to the research we were undertaking with our colleagues at Saclay, Rafael Garcia and others, concerning golf instrument aboard a Soho. So she became interested in that field and undertook a thesis, a PhD thesis, that was defended in 2000, Savita? 2007? Yeah, in Paris, and precisely on the same subject that was the focus of my thesis in '86, the solar G-modes. Of course, with space the data provided by golf aboard Soho. Since then, I've been a close collaborator of Savita for the last 15 years. And she, after the thesis, moves to different places, mainly in the United States. Was working at AJO in Boulder, and later on in the Space Science Institute, also in Boulder. And of course, he moved a little bit to the field of asteroseismology. On the Sun, she was interested on helioseismology and also on the activity, how helioseismology can help us to understand the magnetic activity of the Sun. So Savita is a good example of the link, the required link between Sun and stars concerning activity issues, for instance, or rotation or angular momentum problem. In the last years, she became a very active scientist, very well recognized on the asteroseismology and helioseismology communities, mainly because she's involvement and responsibilities on big consortiums as Kepler, the CASOC, the Apogee, Kepler, Sloan Consortium, etc. And in fact, she was the responsible of the final catalog of stellar parameters of the Kepler mission. We were very glad that Savita decides to come to the IC for the next years, and I hope will end at the IC. And I think he will contribute not only to our group, but as she already proved, groups like the exoplanets and stellar physics groups. So I think it's a very good point that we have Savita with us. So today I think she will summarize all these issues on the Sun and stars connection. Okay.
Okay, thank you, Pere. So hi everyone. I've been working on a lot of things, and this is just one of my main projects that I'm really interested in. So it's understanding how the rotation and magnetism evolves from solar-like stars to red giants. And for this, I've been using mostly Kepler data. So this is, it's not working. Okay. So this is just a brief outline of my talk. So I will start giving a little bit of introduction on the history of what was known on the evolution of stellar dynamics, and we'll show how we can measure stellar rotation using photometric data, and all the results that we had on rotation for different types of stars, from the solar-like stars, subgiants and red giants. And then I move on to measuring and detecting magnetic activity cycles in the stars and some summary perspectives. Okay, so let's start with the evolution of rotation and magnetism, what was known in the past. So in 1972, Skumanich did a couple of clusters in terms of rotation and magnetism and lithium content. And here you have these three variables for two clusters, and you see, I don't know what's happening. Is it working? Oh, okay. And you can see how basically rotation and magnetism decrease with the stars. And Skumanich derived this law that the rotation periods decays as the square root of the age of the stars. Then there were more theoretical works that were done by Waller, McGregor, and Bressner, where we were modeling the angular momentum transferred using magnetic braking with the winds. So that was in terms of rotation mostly. But there is also some dependency that was observed in terms of the stellar mass on how the rotation evolves. So that was done by Kraft in the 60s. So here you have an HR diagram, V minus y versus the surface gravity. And you can see the isochrones for different masses. And the sizes of the symbols represent the rotation periods of these stars, the surface rotation. So the bigger the symbol is, the faster they rotate. And basically you can see there is this limit from where you have more faster rotators and more slower rotators below 1.25 solar mass. This is what we call the Kraft break. And this can be understood easily if you know that so stars more massive than 1.25 solar masses have thinner convective zone, and thus they are less, they go under less magnetic braking because of this thinner convective zone. So they are supposed to have faster rotation periods. In terms of chromospheric activity, there was a study done by Pace in 2013 where he used chromospheric activity indexes and ages from the Geneva-Copenhagen survey for cluster stars and field dwarfs. You have the R'(HK) index, which is based on measurements of calcium HK observations. As a function of the ages of the stars. And one thing you can notice here is that from a given age of around 1.5 gigayear, it seems that there's not so much evolution in the magnetic activity level of the stars. So that's something that's happening in stars in terms of magnetic activity. So one question that we can ask ourselves is the Sun a peculiar star? So in the 1990s, there were observations done by the Mount Wilson provided spectroscopic observations of many stars for a few decades. And Bohm-Wittense in 2007 just represented this diagram, which is the activity cycle period as a function of the rotation period of the stars. And basically you can see that you have these two different branches that come out. So the active branch, called the active one, is inactive branch. And you can see that the Sun is just in the middle. So what's happening with the Sun? But then you can also represent this in a different way, and that was something done by Brandenburg and collaborators. So here you have the ratio of the rotation period and the cycle period of the star as a function of the magnetic proxy R'(HK). So because in this plot, we don't take into account the magnetic activity level of the stars, Here we have a slightly different representation. And the sun is the symbol A here, so it doesn't seem to be so peculiar in this type of representation. And actually, if you use these, so the solid lines here, which are the fits of these two different branches, and if you put them back in this Bohm-Witten diagram, because they depend on the R prime HK, they will not have what Bohm-Witten they showed, that's these two straight lines. There will also be a dependency on the convective turnover time. These can explain why some the outside of these two main branches. Okay, so we still have a lot of issues in understanding magnetic activity of solar-like stars and the sun. We don't know yet what are all the detailed mechanisms of the dynamo. For instance, we can't yet still not predict the cycle for the sun, the future cycles. We still don't know if the sun is a peculiar star, and for this we need to study more data in terms of rotation, magnetic activity, but also have information on the internal structure of the stars. And this is what we can do with Kepler. So these are all the stars that have been observed by Kepler, around 200,000 stars for 4 years. And the other thing that we can use is asteroseismology, because that's the only way we can probe the internal structure of the stars. So here, this is just a basic reminder of what seismology is. So you have the star that's a resonant cavity where eigenmodes that propagate, and they're characterized by L gives the degree L, the azimuthal order m, and the radial order n. And then you have two different types of modes that propagate. You have acoustic modes, for which the restoring force is pressure, and they have the property of being equidistant in frequency. So in this representation, these acoustic modes are reflected on the surface of the star, and the higher the degree is, the more they will be reflected at the surface. Then you have the gravity modes. Maybe I will show this. I think it's working. Okay. For which the restoring force is buoyancy, and these are propagate in the radiative zone of the star. And because of that, they actually become evanescent in the convective zone, and that makes it very hard to measure them at the surface of the stars. And these have the property of being equidistant in period. And finally, you have what we call the mixed modes, which come from the coupling of the cavities of the acoustic modes and the gravity modes. So these are very interesting because they carry information from the core to the envelope of the stars. So as I said, this is the only way to directly probe the deep layers of the sun and the stars, and we can use that to understand why some stars have different behaviors in terms of the magnetic activity. So from seismology, we can use some scaling relations. I will not talk a lot about these. These were based on the sun, and they provide a first estimate of the mass and the radius of the stars. But we can also use stellar modeling, and by using different techniques, either grid modeling or a more boutique modeling of for specific stars, where we fit both spectroscopic observables, but also all the seismic observables, like the individual frequencies of the modes. Then we can have a more precise measurement of the different properties of the stars. So here I'm just showing an example of shown by Le Breton and Goupil in 2014, where they were trying to show how we improve the precision on the age of the stars by using seismic parameter observables. So you have the age here, different cases. Here we are only using spectroscopic observables. And you can see how by using also different physics, we can have a very broad range of ages. And then we start to add some seismic inputs, like global seismic parameters, and then individual frequencies of the modes, and then we start to have more precise measurements of the ages of the stars. So we've done that for a large sample of stars. Now I think we're close to 100 stars, solar-like stars, where we showed that we've improved the precision on the mass, radius, and the ages. But at the same time, because we are doing this boutique modeling, we can also have information on the internal structure, in particular the base of the convective zone, which is one of the key parameters in the dynamo models. Okay, so let's move on to how we can measure the stellar rotation using the photometric data of Kepler. So basically, so this is the sun at a given period of its magnetic activity cycle. And what happens is, because you have these spots crossing the visible disk, you will have a modulation of the light curve that's going to be related to the rotation of the surface of the sun or the stars. Obviously, if the star is not active, then you will have a flat light curve and you won't be able to measure the surface rotation. Then you have different methods that can be used to derive the rotation periods from these light curves. You can use the classical periodogram method. One of the issues with this method is sometimes you will find half of the real rotation period, because if you have spots that are just 180 degrees apart, you will just see half of the real rotation period. So that's why we use two other methods, time frequency analysis based here on wavelets. So you have the period as a function of time, and what we measure is the correlation between this mother wavelet and the light curve. And when there is a high correlation, you have these red, black area. And with this, we can really follow with time how the magnetic activity of the star is changing. And then we can also use the autocorrelation technique that also allows us to disentangle whether we have one or two spots that are, or active regions that are on the surface of the stars. So by combining all these, we have a reliable rotation period measurements of the stars. And we have tested this and validated on simulated data, showing that this technique is one of the most complete that we have for the moment. So that's for the surface rotation using photometric data. But then we can also use asteroseismology, because rotation has an effect on the modes. So if the star is not rotating, you have, for a given mode, you will just have a single peak for the L=1 or the L=2 modes. But then if you add some rotation, you will have a splitting of the modes. There will be a lifting of the degeneracy. And for the L=1 modes, you will have 2 components. For the L=2 modes, you will have 3 components. But there's some complication that also comes from the inclination angle of the star. It's similar to the V sin I that we have. So given, depending on the inclination angle of the star, you will see different ratios in the amplitudes of the components for a given mode. And obviously, if we observe, then you won't see the rotation and you will have single peak. So I'm going to move on to what we managed to do on solar-like stars observed by. So we first started to look at stars for which we had detected oscillations, because these are the best characterized stars we have in the Kepler sample. So we had around 500 solar-like stars where we had acoustic modes detected. And we applied our pipeline to measure the surface rotation and found reliable values for 300 stars, which are represented in this kind of modified HR diagram. And then you can divide these stars into 3 groups: cool stars, hot stars, and subgiants. And here you have the distribution of the rotation periods for these stars. One thing you can notice is that stars are the stars that are rotating faster, which is what we were expecting, and then stars that present slower rotation periods are the subgiants, given the evolution stage of these stars. It's something we would also expect. And yes, so one thing you need to keep in mind is that we have a bias sample because the star needs to be active in order to measure the rotation period. So from there, we had a subsample of stars for which we had done the boutique modeling to measure the precise ages of these stars. So we could test whether our sample agreed with what Skumanich has shown 40 years ago. So you have the rotation period of the stars as a function of the ages for around 12 stars. And basically, we found that we have the same exponent on the age of the star as what Skumanich has shown. So that is a relief, at least that's still working. But if you look into more details, there's something weird that's going on. So here you have the rotation period of the stars as a function of the ages for 3 different ranges of effective temperatures. And so in black, that's what you would expect with a model that's similar to what Skumanich has shown. So an angular momentum transport that's based on the wind magnetic braking. And one thing you can notice is that, especially here, stars seems to be rotating faster than what we would expect from this backline. You can also see it here. So this means that at some point the magnetic braking had stopped and stars keep rotating fast. So in this paper, Van Segers and collaborators, we just tested a new model where we stopped the magnetic braking in the model at a given Rossby number. So here it's around, we found the best results for a Rossby number of 2.16. And these are the results from this new model where we found a better agreement between the observations and the model. So basically what we can say is that for middle-aged stars, it looks like when they pass a given Rossby number, the magnetic braking stops. And here you can see that for the sun, it seems to be just at the edge of this transition phase. The other thing it's pointing out is that gyrochronology cannot be applied to all the stars, and you have to be careful at which stage of this evolution it is. So is the sun in transition? So that's still a question, and that's also something that can be seen when you look at the magnetic activity level of the stars, of the solar analogs. So these are solar analogs that were observed with the Mount Wilson and Kepler. You have the log R prime HK, the rotation periods, and maybe you have heard of the von Preston gap. That is where we have had this gap in terms of number of stars with a given R prime HK number. And this gap, if you represent it in this plot, is just where you start to have stars for which the rotation period is in a broad range, but the magnetic activity level is pretty low. So this also seems to show that the sun is indeed in this transition phase where the magnetic activity has reached a certain level, and so this is a work in progress, but we need to understand what's going on. But there's definitely some transition going on in the sun. So then we also studied some G-type stars with a student in Paris, Thibaut Dumont. So we studied 34,000 G-type dwarfs here with the Kepler data. And this is still a preliminary work. So we used data that was filtered with a 20-day filter. So whatever is happening above 20 days is still very doubtful. We need to use other filters with 55 or higher filters to be sure that what we are detecting is the real rotation period. So we've been using some different criteria to select automatically the reliable stars, rotation periods of the stars. And so far it looks like we have around 3,000 stars with reliable rotation periods and 4,000 promising stars. So basically, yeah, here on pretty fast rotation because of the filter that we are using, but we need to go further with different filters. So then we can move on to subgiants. Okay, so for this, I'm going to focus a bit more on the internal rotation of the stars. So this is what we know for the Sun. This is just to show you the state of the Sun for the moment in terms of internal rotation period. So you have this differential rotation in the convective zone, and then a more solid body rotation in the radiative zone. And for the core, so that was done. But recently there was, so for the core we don't have a rotation period measurement, but recently there were individual gravity modes, so the gravity modes that propagate in the core of the Sun, that were detected by FOSAN collaborators, showing that the average core rotation rotates 4 times faster than the surface of the Sun. So this is what we know for the Sun. But then for subgiants, we had with Kepler a lot of interesting results because the subgiants have mixed modes that are propagating like gravity modes in the radiative zone and then as acoustic modes in the envelope. So they allow us to probe really different regions of the stars. And here you have the splittings for a given star at different frequency regions. And you can see that the separation between these two components is slightly different when you go at a different frequency regime in the star. And so if you see here, so this is the splitting as a function of the distance to the helical theoretical mode that we have. So these modes are more acoustic-like modes. These are more gravity modes. And you can see this slope in the splitting. So if you do some kind of inversion, then you will have this kind of profile where the core is rotating 3-4 times faster than the surface of the star. Okay, I have to tell you that you shouldn't believe what's happening too much in between here, because we have basically points around here and points around here. This is more like a smoothing effect of the inversion. So that was for one star, and then so De Hovels and collaborators extended this to 6 other subgiants. And you can see how the rotation rate of the core is increasing with time, with the evolution of the star, whereas the surface, the envelope, is slowing down. Okay, so now we can move to red giants. So in Kepler we have 20,000 red giants for which we had detected acoustic modes. So here you have a representation of the HR diagram. Here we use 17,000 stars, and for which we had more than 4 years of data, and that were observed with a cadence of 30 minutes. So basically in blue, that's where we found the blue dots are the stars for which we found a reliable rotation period. And this is a sample of 500 stars. So first we did some automated detection of the rotation periods because we couldn't go through the 17,000 stars to get the light curves. But that was based on what we knew on solar-like stars. And that gave a sample of 900 stars, and then that's where we did a visual check of all the wavelet analysis and autocorrelation analysis, and that's where we ended with a sample of 531 stars. The of these rotation periods. So in blue, these are the reliable rotation periods that we found for these red giants. But in some of these stars, we might still have some pollution because sometimes we have a high crowding in the Kepler pixels, so we might be measuring the rotation period of a nearby star. And we also have stars in which the rotation period was shorter than the breakup velocity, so these were also discarded from the sample. So at the end, we end up with 361 stars with the reliable rotation periods. So why do we have so many rapid rotating red giants? You would expect them to be rotating pretty slowly, given the expansion of the envelope. So we can look at because we have seismology, we have the masses of these stars. So we can look at a subsample of low mass clump stars, so masses below 1.1 solar mass. And these stars should be rotating pretty slowly on the mate sequence because they're going through magnetic braking. They have large, thicker convective zones. So these low mass stars here shouldn't be rotating fast. So one way of explaining the fast rotation periods we get is that they go through a merging with another star. So there were some theoretical works that showed that maybe 7% of these low mass stars should be undergoing mergers. And our work shows that it's actually the case for 15% of the stars. So maybe we are still underestimating the number of stars going through mergers. The other subsample of stars we can look at are the intermediate mass stars, masses above 2 solar mass. And if you assume that there's a solid body rotation, normally more than 50% of these stars should be fast rotators, but we only find around 2% of those that are very fast. So this means that we need to investigate more what's happening in terms of, yes? These were mostly outside clusters. It's field stars, yes. So that means that the angular momentum process that we are using is not completely understood, and maybe they are going through some radial differential rotation that we are not including in the models. So I was talking about the internal rotation of the subgiants, so we managed to do the same thing for red giants. So that was done for the first time by Beck and collaborators, where we showed that of these red giants seem to be rotating 10 times faster than the surface of the stars. And then there were some modeling, stellar modeling that was done for these stars. And basically, so this range is where we obtained the rotation period of our observed red giants. And the black line here is what the models give. So basically, the models are definitely rotating too fast in the core compared to what we observe in these red giants. So we need some additional physical processes like internal gravity waves, magnetic field that's not included in the models that could help us decrease the rotation rate of this model. Okay, so then this was also extended in more than 300 red giants by the Moser and collaborators. And they showed that there was indeed a spin down of the core during the evolution. Is it work? Okay. And Spada and collaborators did some modeling to try to reproduce what we're observing, and they were using some kind of angular momentum diffusion coefficient, and they seemed to be able to reproduce some of the observations with the new model. However, so recently there was a work done by Jean and collaborators where they extended the study for 700 red giants, and they don't seem to see this spin down so clearly, and so this is still an open question. We still don't know what's happening. So now we can move on to the secondary clump stars. That was also in our sample. So this is still a work in progress, but basically Tyre and collaborators we are doing some modeling to study these secondary clump stars by using 3 different models. So we have one where the core and the envelope are decoupled. So this is what we would expect in terms of the core rotation of these secondary clump stars. Basically, you can see that it doesn't reproduce the observations, which are in red. So the observations seem to suggest that what's happening in these red giants is something in between having a radial differential rotation and an enhanced loss for a rigid body angular momentum transport. Okay, so that was in terms of rotation. So let's move on to the magnetic activity of the stars. So for the surface magnetic activity, we have defined a new activity index using the Kepler data. We call it the SPH, the counterpart of the S index from spectroscopy. So basically it's the measurement of the standard deviation of the light curve from Kepler. So this is a typical Kepler light curve as a function of time. You have almost 4 years. And we take a sub-series of length, an integer times the rotation period of the star. Whoops. Which gives us this standard deviation as a function of time, and then we take the mean value of this standard deviation, which gives the SPH. So we compared this measurement with, for the Sun with classical proxies of magnetic activity. So here you have, in blue, this is the SPH, obtained with the Virgo instrument, and in red you have up here the sunspot number, calcium HK, the flux at 10.7 centimeters, the mean magnetic field, and frequency shifts. I'll come back to that later. But basically, you can see that there's a pretty good correlation between our SPH and all these classical proxies. So we can validate the way we are measuring the magnetic activity of the stars using this proxy. So from the sample of stars where we had measured the rotation period earlier, we measured the SPH. So here you have the SPH as a function of the rotation period, and here you have the range of the SPH for the Sun between minimum and maximum activity. So you can see that still most of our stars are in the same range as the Sun. So in that sense, the Sun doesn't seem very peculiar compared to other solar-like stars. And one thing we also need to keep in mind is that these observations were done only on 4 years, so we don't know exactly when in the magnetic cycle we were when we were doing the observations. And the other thing that can bias our observation is the inclination angle of the star. Because if the star is very inclined, we might not see the spots as much as if the star was like the sun at a 90 degree. So basically this is like a lower level of the lower limit of the magnetic activity of the star. Okay, so then we can also start to look at the activity cycles. So this is just to remind you the Bohm-Beatency plot, and because we are doing observations up to, of 4 years with Kepler, we expect to detect magnetic activity cycles for rather fast rotators. So here we focused only on stars that were rotating faster than 12 days. And which are here. And I'll tell you why I'm talking about the Jungle Book. It's because we have so many stars, we give names to our stars. So one of our colleagues had his son interested in Jungle Book, so we were giving the Jungle Book characters name. So this is Ka, which is basically it's an F star with a rotation period of 2.2 days that you can see around here. And if you project this wavelet power spectrum on the time axis, you see this very nice modulation that looks like a cycle. Okay, so I was like, oh yeah, we have a cycle, except that when we looked into more details on how the frequencies of the rotation period was changing with time, we had these two strong peaks that were stable for a long time and creating a beating between these two frequencies that was exactly the period of this modulation that we were seeing. So we didn't have a cycle, but we managed to see that there were very long-lived active regions at the surface of these stars, creating this behavior. So it was most likely to be active longitudes, but maybe it's also a close companion that's creating these spots at the same during all this the observations of Kepler. So this is another star. This is my favorite star, Sherkan. It's also an F-type star with a mass of 1.4 solar masses, a very thin convective zone, and a rotation period of 2.5 days. And here we have, again, the projection of the wavelet power spectrum on the time axis. And you can see this very nice cycle here. Another thing you can see is we have a kind of butterfly diagram where you can see that the rotation period at low activity is higher than at high activity. So the rotation period is changing with time. Here again, if you look into more details at the projection on the during the maximum activity, you can see these secondary modulation, which is again coming from the beating of two very close frequency in periods, suggesting here again we have long-lived active regions. These are just examples of stars where we had some weird behavior in their activity cycle. This is a work that I've been doing with a student in the US. So this is just to show you that lots of things are happening in the Kepler targets in terms of magnetic activity. So this is, okay, so now I'm moving into using asteroseismology to detect magnetic activity. Okay, so this is the sun, the Virgo photometric observations, the wavelet analysis, the projection where we can see the beautiful cycle for the sun. And what we've observed is that for the sun, the acoustic modes are affected by the magnetic activity. So here you have the amplitudes of the modes as a function of time, how the frequencies are changing as a function of time, and in red, the red line is the sunspot number. So you can see how the frequency shifts are correlated with the sunspot number, whereas they are anti-correlated with the amplitudes of the modes. So basically, magnetic activity, when it increases, suppresses the amplitudes of the acoustic modes. So we did a similar analysis with the core target HPD 49933, which is an F-dwarf. It was observed during 2 campaigns of CORO. And so we had detected oscillations for the stars. We also had a rotation period of 3.4 days. And when we looked at the temporal variation of the amplitudes of the modes and of the frequency, we found this very nice anti-correlation between these 2 parameters, just like the Sun. So this was the first other star than the Sun where we detected the same behavior, suggesting there is magnetic activity on this star, and something similar than what happens in the Sun happens on this star. We also had some spectroscopic observations here at the in Cerro Tololo. So here you have the S-index, where you can also see very nice change in the S-index. Unfortunately, we don't have enough observations to really measure a cycle period. But yeah, that was a start. We also have more stars, but which we did this similar analysis. This is Mowgli, one of the other stars, where we can see, so this is the SPH variation as a function of time, and the frequency shifts in blue, and you can see this very nice correlation between the 2. And this star is very interesting because it's very young, 1 giga-year, that's from asteroseismology, and a rotation period of 11 days. And then more studies have been done with this from these 2 in these 2 other papers. Okay, so now this is the last thing I'm going to talk about is Doris, this other star Doris, which is solar analog. So these parameters were obtained with asteroseismology, close to 1 solar radius, 1 solar mass, an age of 4.5 gigayears. But one difference between this star and the Sun is the metallicity. So this is a very high metallicity star compared to the Sun. And for this star, we were lucky to have a lot of observations done. So we had some chromospheric emission measurements here. This is for Doris, and the right panels are for the Sun. And here you have the photometric flux of Doris, the frequency shifts. Okay, this is maybe you don't see it so much, but there is definitely what is it? An anti-correlation between the frequency shifts that are increasing here and the amplitudes of the modes, just like the Sun, and this is the SPH that's correlated with the frequency shifts. So one thing that you can notice is that the chromospheric emission is actually much stronger than what we observe in the Sun. And the cycle period is also shorter. It's around, I think it was around 8 years. And one way of explaining this is just the effect of metallicity. So because we are increasing the metallicity of the star, we are increasing the opacities, and the criteria to have the convection started will happen deeper in the star. So the convection zone of this star is 8% deeper compared to the Sun. And when you have a deeper convection zone, you will have a longer convective turnover time, which will lead to a stronger differential rotation, and that's a stronger dynamo, explaining why we would have this stronger chromospheric emission for the star compared to the Sun. Okay, so that's another example of what we can do by combining asteroseismology and spectroscopic observations. So that leads me to the summary. So we've seen that for solar-like stars, if we compare them to the sun, they have similar magnetic activity levels, but stars older than the sun seem to rotate faster than what's expected from the previous models, suggesting that there's a magnetic braking that stops for a Rossby number of 2. Also, there seems to be a transition phase leading to longer cycle periods. I didn't talk about this, but this is a work done by Metcalfe and collaborators. Then for the subgiants, we managed to have surface and internal rotation rates. The models don't predict still these observations. And same thing for the red giants, where the core rotates 10 times faster than the surface. And now we have around 400 stars for which we have measurements of rotation periods. And then we have these intermediate stars that seem to rotate slower than what we expected, suggesting that there is some core envelope coupling, and we also have these fast rotations in the low mass stars that could be explained by large refraction of mergers. And for the future prospects, well, we still have K2 running, for which we have 70 days of continuous observations, for which we can do a little bit of rotation period measurements, not necessarily magnetic activity cycles, because 75 days is very short. We also have TESS coming, and that would be interesting in terms of magnetic activity for the ecliptic poles, for which we will have 1 year of data in average. And then in the far future, we will have Plato. So just to finish, I told you this is just one of the projects I'm working on, but these are other things. I'm also interested in convection granulation of the stars, making the solar-stellar connection. I've also been working on galactic archaeology with apogee combined with asteroseismic observations, because we can have more precise ages of the stars in different directions of the galaxies. This is an example of so these are stars that were red giants that were observed by Kepler. In green are new stars that were misclassified and happen to be very far away from us. So they're showing that we can really study the asteroseismic properties of stars far away from the solar neighborhood. And then obviously I'm applying this to exoplanets characterization. So that's all. Thank you.
I think we have some time for questions. Unfortunately, what we don't have is battery for the microphone. So maybe you can use this one and I can take the other one. Is this thing working? Yeah. So can I? So, questions?
Thanks for a very nice talk. Did I get it right that there is some confusion as to whether the rotation of the core spins up when the stars above of the main sequence? That there were some results that suggested the contrary? Do we need more data here, or is just some?
It's just so it's more data, longer observations. So because the work done, the first work by Moser was based on, I think it was 1 or 2 years of observation, 2 years of Kepler data, and now it's more than 4 years. And then so it's her student who's actually doing this work. So she applied a slightly different technique, and that's where she's finding these different results.
Okay, but you have more trust on the other results that show, according to the theoretical models, that the cores spin up.
I wouldn't be so sure 100%. But I mean, the models were also kind of tweaked to try to reproduce the observations. So yeah, I would say wait for the paper to come out, the new paper. And
thanks. Any other question? Well, I have my own. So you didn't mention anything about differential rotation. Do we know something about the differential rotation of all these stars?
Do you mean latitudinal?
Yeah.
Yeah, that's something. Okay, so yeah, I should have shown another paper, but there's some work going on. So basically, it's very hard from the Kepler observation. So what we basically are looking for is, when you look at the periodogram, is to have like a bunch of peaks instead of just a single peak for the rotation periods, or a broader peak showing. So when we do our measurements, we do have in the, let me see. Okay, so here, for instance, so maybe this would be one of the cases where you have some differential rotation, because depending on the magnetic activity level, the rotation is changing from 3-ish days to 2 days. So
yeah. But can it be a good summary, say that we still have very little knowledge about how the differential rotation happens in other stars that it's not the sun?
So there was a paper by, I think it was Reinhold, a few years ago. So they were trying to see how the second harmonics of the rotation period was compared to the first harmonic, and they were using this to measure differential rotation. I'm still a bit dubious about what they were finding. Then we can also use asteroseismology. There were a few works done on a few stars where they were trying to see how, because the different modes will probe different regions on the stars. But it's still a work in progress. It's not happening too much yet.
So I think we should finish here. Thanks our speaker, and welcome her, because I mean, you mentioned at the beginning, but she's going to be here for long. So I mean, if you have questions or when I talk to her, she will be around. Okay, thank you.
Studying with the last student, we have been studying the time series of the Chromospheric activity indicators in spectroscopy, high resolution spectroscopy.
Okay.
We found different correlations with the level of average activity and so on. And we have been doing this for different spectral types. All the stars are dwarfs, but